Good morning. Today we're going to be working, as you see, on applications with linear and rational equations. Problem-solving strategies. Well, if you've seen one of these lists, you've seen them all. You read the problem carefully, determine what the problem is asking for. That's probably the singular most important item in this whole list. Then you pick variables to go with the unknown quantity. Now, speaking of variables, the way you determine what variable should be X, the unknown, is the one that tells you nothing about it. Somewhere in the problem, it may give you some comparative information for other numbers or values, but there will be one number that they don't tell you anything about. That's always your variable X. You write an equation that represents this. When you write the equation, of course, the equal sign is represented by verbs in the language, is, are, and so on. After you've got it solved, then you look to see if your answer makes sense. So, Carlos borrowed a total of $8,000 from his mom and a bank, together $8,000, to start a food truck business. The bank charged 5% interest. His mother gave him a 1% sweetheart deal as long as he was willing to call her more often. The total interest after a year was $280. So, how much did Carlos borrow from his mom? How much did Carlos borrow from the bank? Well, let's decide what our X is going to be. They tell us in this, let's see, they got the 5%, they got the 1%. The total was after 8,000. They tell us that the total borrowed was 8,000. Well, we actually on this problem could let either the mom or the truck be the X in this case, but we're going to let the mom be the X. If mom is X, then the bank is the $8,000 minus what mom loaned, okay? And here's our fundamental theorem. I equals PRT, interest equals principal times rate times time. Here's our fundamental question, or our fundamental problem. If we find the interest on mom's loan and the interest on the bank loan, that's got to be the $280 that they told us. Now, how do we do that? P, R, T. P, R, R, T. And that's the total interest. Okay, so the interest from mom's loan plus the interest from the bank loan equals 280. Simplified, we multiply this out here and here and just bring that down. Now, we didn't show a step in here. They skipped a step on you. What they did was they took this and this and combined them for that. Then they moved this 400 over to the other side, resulting in this negative 120. They divided both sides by negative 0.04. They didn't show the cancellation here. Here we've got that. If you want to take a shortcut, you can move this decimal over twice, move this one over twice. Okay, 4 goes into 12, 4 goes into 12 3 times, 3,000. Just a simple way of doing that long division. So what this is saying is mom loaned Carlos $3,000. Now, if she loaned him 3,000, then the bank loaned him 8,000 minus 3,000, or in other words, 5,000. And that solves our problem that it asked for in the original problem. So here's your final statement, your labels. Remember, if you don't have labels on your tests and quizzes, that will be a deduction. What about mixtures? Mixtures fall into a pattern. Actually, it's the same pattern where we had here with the percentages. Now, in this case, I went a little too fast. They got some party, they want to make some snacks for a party. They combine low-fat trail mix and a tasty candy mix. They want to know how much of the 10% trail mix you have to mix with 4 ounces of the 40%. So we know how many ounces of the candy mix we've got. We don't know how many ounces of the trail mix we have. So therefore, the trail mix, how many ounces, will be the X in this problem. Now, Alex that we use likes to use charts, so I'll go along with theirs. The amount of mix for trail mix we said was going to be X. The amount of mix of candy mix we know is going to be 4. Well, the total mix will be however much trail plus however much candy to get the total mix when we get our 12%. The trail mix is 10%. The candy mix is 40% times the 4 ounces. 10% times the X ounces. And finally then, our 12% times the combined ounces. So this is fundamentally our equation. In some respects, it's like the problem that we just finished, where we put the percent times the variable, the percent times the other value, and the percent times. So with that, here is our equation. They chose not to eliminate the decimals. I would have cleared the decimals on each one of these by moving the decimal over 2 places. Now what they did was and they didn't show this, but they took this 1.6 over to the left by adding negative 1.6 and adding negative 1.60. At the same time, they also took this over to that side by adding negative 0.12x and negative 0.12, and let's fill out a 0 there, x. Now, when they do that, you see we end up with negative 0.02x here, and this becomes negative 1.12. The last step that we need to do here is divide both sides by negative 0.02x. So they did that on both sides here and here, resulting in this calculation. You could do it in a calculator, or move this over 2, move that over 2. So we're now dealing with 112 over 2. Well, 2 goes into 2 once, 2 goes into 112 56 times. So that's just a mental math way of working that problem. Finally, what have we got? She needs to put 56 ounces of trail mix with her 4 ounces of candy mix to have a total of 60 ounces of her snack mix. Here's another mixture problem that was real life for me. That's my grandson when he was about a sophomore in high school. We bought this Mustang. It was kind of plain and ordinary. He wanted to put a set of rally stripes on it. So we ordered the stripes. These are called Eleanor stripes. And to install them, you needed a solution of 70% isopropyl alcohol. If you used a stronger solution than that, the instructions said it could damage the glue on the back of the striping material. So we had to dilute the 91% alcohol we found in the store. So how much water did we need to add to this 16 ounces? That's the question. So how many ounces of water do we need to add to 16 ounces of 91% alcohol to create a 70% solution? And then how many total ounces would I end up with? Let's let X equal the amount of water. X plus 16 equals the total ounces. So 91% times the 16 that we know we have, plus 0% times the water ounces equals a 70% solution times the total ounces. I'm going to clear the decimals by multiplying everything by 100. So I get 91 times 16 plus 0 times x equals 70 times x plus 16. And you multiply these two out, you get 1496. Or you get 70x and 1120. Well, we want to subtract 1120 on both sides because our variable's on the right. So we're getting rid of these numbers on the right by adding their opposite. There should be a negative sign right here. So we add a negative 1120 to both sides, resulting in 336 equals 70x. Now we divide both sides by 70. So we end up with 4.8 ounces of water that we have to add to the 16 ounces of alcohol. Our total solution will end up being 20.8 ounces, which we put in this bottle. And as you can see, I labeled it as alcohol. Personally, I think his car looks much better. We also have these headlights compared to the other. We have grills and a WkO2 set of levers on the back, and he thinks it's the coolest thing ever. Another solution problem, how much 4% acid solution should be mixed with 200 milliliters of a 12 to make a 9. Okay, in this case, the ounces of 12% is 200 ounces. Okay, the ounces of 4% is don't know ounces. Okay, so that's what we gathered from that. So now we'll write our equation. 4%, 0.04 times x plus 0.12 times 200 equals 0.09, excuse me, times x plus 200 times 200, 9% times x plus 200. Okay. Cleared the decimals. Take the numbers over, take the variables over by adding their opposites. and I get negative 5x equals negative 600. So I divide both sides by negative 5, and I get 20. D equals RT. A little bit of a primer about D equals RT. Distance, rate or speed, and time. Okay? Now, you can have variations of this. If you want to know how long it takes you, then divide both sides by the rate or the speed, and that'll tell you how long it takes you. If you want to find out how fast you need to go to get in a certain amount of time, you take distance divided by time equals rate. Those are the three variables of this that you can use for distance equals rate times time. Now, given that, a simple example, if it's 500 miles to Denver, and you are going 50 miles per hour, then your time has to be 10 hours. Okay? Well, you would use this if you wanted to know how long it took you if you were going 50 miles an hour. 500 over 50 equals 10. That's how I got this 10 miles for 10 hours. Okay, what if I wanted to know how fast I needed to go if I wanted to get there in 8 hours? 500 divided by 8 hours equals, well, 8 goes into 50 6 times with 2 left over. 8 goes into 20 twice, okay, with 4 left over. So you would have 62 4/8, or in other words, 62 1/2 miles per hour that you would have to drive to make it in 8 hours. Now that means constant speed, no slowing down, no stops for rest, no stops for refreshment, okay, no stops for gas. So if you want to get there in 8 hours, you're going to have to drive faster than 62 1/2 mile an hour. You're probably going to have to drive 70 or even 75. That way, when you're stopped at 0 miles per hour, they will offset for an average of that. When I'm doing long trip planning, I plan on an average speed of 50 miles an hour, even though I drive 70, even 75, sometimes 65 to 75. And that way, it allows for stops and still making it in that general estimated time. Now, to this problem, our distance equals rate times time. It tells us they leave at 7 a.m. going opposite directions. It takes him 30 minutes, takes her 20 minutes in her direction, okay? Her speed is 7 less than his. We don't know anything about his speed. So his speed is ultimately going to become our x, his speed. Now, if they're 6 miles apart, what's the average speed in miles per hour for each person? Okay, x is Daryl's speed. X minus 7 up here, right here, hers is 7 less. Hers is x minus 7. We're going to do a little bit of time conversion. 30 minutes is a half hour, and 20 minutes is a third of an hour. That keeps our time factor much simpler. So, Daryl's speed is x. Cynthia's speed is x minus 7. Daryl's time it takes him is a half hour. Her time is a third of an hour. So the distance he travels is 1/2 x. The distance she travels is 1/3 times x minus 7. D equals RT. Okay, this chart's going to transfer to my next slide. So here's what we had from the previous slide. Now, to solve this, it says they're 6 miles apart. The total distance is Daryl's distance plus her distance. Well, 6 is equal to his plus hers. And as we look at this, we've got a common denominator. So I multiply each side by the common denominator 6. This produces 36. Distributed here gives me 3x. Distributed here gives me 2 times x plus 7. I distribute that 2. I combine terms, 2x and 3x is 5x. And at the same time in this step, I added 14 to both sides of this equation to move this 14 over here, which gives me 50 equals 5x here. Divide both sides by 5, and my resulting answer is x is 10. What that means is Daryl is going 10 miles an hour. So if Daryl is going 10 miles an hour, then logically Cynthia is going 7 less, or 3 miles an hour. So 10 miles an hour, 3 miles an hour are their relative speeds, which answer the question. Rate of work. In the handout packet that I've given you, there is a formula for work rate. One whole job over the time it takes the first person plus one whole job over the time it takes the second person equals 1 over the combined total time for both of them working together. We're going to use this formula in this problem to find out if Malcolm and Jamal can meet the requirement of doing the job in under 2 hours. So therefore they can earn the $100. So let T equal the time between together. Once again, we're going to have Malcolm's speed plus Jamal's speed equals the combined speed. His job over 3 hours. Jamal over 5 hours it would take him equals 1 over the total hours. Here again, the formula we carried from the previous slide. In this case, common denominator is 15t. So I multiply both sides of this by 15t to eliminate the denominators. I multiplied and canceled or factored, resulting in 5t. 15t divided by 3 is 5. 15t divided by 5 is 3. 15 over t times t's cancel, so you just get 15. Combine the two variables, the two t's, divide by 8, and you see they got it in 1 7/8 hour combined. That meets the requirement of doing it in less than 2 hours. So yes, they can do this job for $200. Now, how long is 1 7/8 hours? Well, 1/8 of 60 minutes. So 60 divided by 8, about 7.5 minutes roughly. So for each one of them, or the other way to think about it is about an hour and roughly 52, 53 minutes. So yes, they can do it in less than 2 hours. Here's another one. At this point, I'm not going to do that. When we're doing, here's the work on this one. So I guess I will do it. Sheldon, Penny, total job. 30 minutes in office, 45 minutes in office. We do the work in common denominator. In this case, is 30 times 45. So we took 30 times 45 in each case, and t times the 1, 30 times 45 times t times 1, 30 times 45 times t times 1. Here, the 30s will factor out, the 45s will factor out, the t's will factor out, and you end up with 45t plus 30t equals 30 times 45. A little bit of arithmetic, you end up with 75t equals 1350. Divide by 75. You can work this by reducing, or you can do it by long division. In either case, that's saying it's going to take 18 minutes per room. Now, that wasn't the whole thing. There's a question B in here. This is to do one office. Okay? But question B, which is covered up on this page, says, how much would it take them to do 16 offices? So here, 18 times 16 would give you that, or 288 minutes, which is 4 hours and 48 minutes, or 4 3/4 hours. So that's what they would have to do it in to do, or would expect to do their job in. All right, we're ready to go into complex numbers. Here are the various concepts within this topic. We will get simplifying them right now. We may touch on write them in A plus BI format. Now, associated with this, you need to understand square roots. So there is certainly a square root. Okay, in this chart, I don't have this chart in your packet of supplemental materials that I've given you, but this chart would be probably a good one to memorize. Now, there are some things that need to be added here. I need to put a square root symbol over each of these. Okay. Now, this side is the set of perfect squares. Okay. This side is those perfect squares taking the square root. If you notice, if 6 squared is 36, then the square root of 36 is 6. And that's what we call the prime square root. Okay. The positive side, and we'll talk about the negative side later. 10 squared is 100, so square root of 100 is 10. Now, I've included 12 squared, 13 squared, 169. I would expect probably on my test or on the final that you're going to have some problems where you're going to need to take the square root of 169, whether that's using the quadratic formula or whether it's doing something else. Almost consistently it has been 225, 15 squared. That's one that shows up sometimes. You definitely need to know that 20 is 400 is 20 squared, and that 25 here is 625 squared is 625. Now, the important about this and how this relates to imaginary numbers is the imaginaries follow exactly this same pattern. There are two primary rules in square roots, in imaginaries. Define the square root of -1 as being equal to I. First. The second, following with this, if the square root of -1 is I, then I squared should be -1. The same identical pattern that we've had on all of these others. So those are the two fundamental rules that deal with imaginary numbers. Now, here are some examples. What if we wanted the square root of 25? Well, literally, 5 is the square root of 25 because 5 squared is 25. So is -25. -5 is a square root of 25 because -5 times -5 makes positive 25. Now, again, most of the time, we use the principal square root, which is the positive side. But later on, when we are doing operations and we take the square root of both sides, then we're going to have to show a plus or minus because of this duality. Likewise, on 49, 7 and -7 could work. But what about -9? -9 does not work this way. Now, square root of 9 is 3, but that negative under the radical means that we've got an imaginary number hidden inside. So the first thing we have to do is, if I were doing this problem, and I've got it over here, but at any rate, what I did here first was I extracted this 9 over here to this 3. And I left square root of 1 because there is a hidden 1 here times this 9. Now, the square root of -1 extracts 2i. So the answer in this case is 3i. Here, I showed that I extracted 9 equals 3. Then that would extract to I times 3, 3i. Just two different orders of doing it, but the same solution. So there are no real valued square roots of -9. Anything with an I in it is a value that you cannot graph. It's there, but you just can't graph it. Let's simplify some imaginary numbers using those primary rules. If b is any positive number, and we've got this, basically we're going to extract this negative to an I. Then, if we can take the square root of b, we will. Maybe we can, maybe we can't. Now, let's work these. -100. First, we extract the I. Which leaves us square root of 100. And we get 10i. When we extract the square root of 100 is 10. -36. First thing we're going to do is extract the I, then take the square root of 36, which is 6, so 6i. Square root of -6. We extract the I, and 6 won't break down. We could break it into 2 times 3, but that would not help because neither of them is a perfect square. So we just leave it I square root of 6. In this case, square root of 21. Once again, we extract the 21, 7 times 3. Neither of those two numbers are a perfect square, so we can leave it as square root of 21. Negative 50. Now, negative 50 is a little more special. It's got an extra step in it. We're going to extract the I. 50 in itself is not a perfect square, but hidden inside that perfect square, or hidden inside that 50, is a perfect square. You know, there are 3 laws of radicals. The first one, thou shalt not leave a hidden perfect square under the radical. And then there are 2 others. Thou shalt not leave a radical in the denominator. Thou shalt not leave a radical inside, or a fraction inside a radical. Now, right now we're dealing with that first law. You can't leave a hidden radical inside. 50 happens to be 49 times, or excuse me, happens to be 25 times 2. 25 is a perfect square. So in this case, we break it out. Now you could show it that way, or you could show it this way. Both of these under the one singular radical. In either case, you're going to take or extract that 25 from under the radical. When you do, you're going to get a 5, whether you do it this way or whether you do it out of there. And of course, here's the I we just brought down. We got a leftover of square root of 2. And that's the way it's got to remain. Negative 48. Well, we can pull the I out of it quickly like we did the 50. 48 has several ways it can break down. 6 times 8, 12 times 3. However, the 12 times 3 has a hidden 4 in it. But the easiest way on this one is to break it down into 16 times 3. And again, these could be under a single radical if you chose. Square root of 16 is 4. We can't do the square root of 3. It's a leftover. So we have 4i square root of 3. Negative square root of negative 16. This negative out front is just going to be carried down to our final step answer. Now, in this case, first thing we do, we extract that negative. Square root of 16 is a perfect square, so it becomes 4. Now, the 16 became 4. Here is the I, and here is that negative that we just brought down. Okay? Very quickly, these 3, 81 is a perfect square, so the answer is this one we did just a moment ago. It's 5i square root of 2. 11, not a perfect square. So the answer is just simply I square root of 11. Now we've got these. When you multiply and you have any negatives in those, you must extract those i's before you deal with the numbers. In this case, it results in an I here and an I there. These together are going to become I squared. We still need to take the square root of 4, which is 2, the square root of 25, which is 5, and simplify that to 10I squared. Now, there is an alternative way we could have shown this. We could have shown this as I squared square root of 100 if we chose. And square root of 100 is 10. So that's just an alternate way we could have done this problem. Now, we're not finished with this, because this is I squared, and we have the rule that I squared equals -1. Then we have to convert this to a -1, which they've shown here. So our final answer then is -10. Another one, similar to the last. We've got a pair of imaginaries to extract. Now, 10 is not a perfect square, and neither is 40, although it's got a hidden 4 in it. So let's multiply the 10 and the 40. This is similar to what I did before and got the 100. 400, on the other hand, is a perfect square. Square root of 400 is 20. So we take that, we convert this I squared. Okay, we convert this I squared to -1, and then our final answer then is -20. We got a division. Now, division, a little bit different from multiplication. There are actually a couple of ways we could work this problem. The first way we could do this problem, extract the I, we've got this. Now, what they didn't show was perhaps this step. Because we can convert this to this. 98 divided by 2 is 49. Square root of 49 is 7 with the I. Okay? Let's look at these. Here, I squared, 4, 7, so 28I squared gives you -28. Here, I squared, square root of 20, which is equal to I squared, square root of 5 times 4. 4 will extract to a 2. So we got I times 2 radical 5. And so our final answer then is 2I radical 5. Over here, we can put these under a single radical, -48 over -3. In division, those can cancel because you're dividing them. 3 goes into 48, 16, so this becomes square root of 16, which is 4. Now, what if you did convert those to i's first? You can do that. And here's why you can cancel it on these. If you did convert those negatives to an I first, you would have this over this. I divided by I is 1. And then you would have 40 over 3 is 16. Okay? And then square root of 16 is 4 again. So in either case, either the i's or underneath, you can cancel them. A plus bi, that's the standard format for complex numbers. Now, in this format, A is the real number portion of it, bi, b being a real number, and the I goes behind that. So, if all we have is a -5, that's just a real number component. So technically there's a plus a 0i, but we never show that. In this one, 17i, technically there's a hidden 0 plus for the real number component. But typically we would just write our answer as 17i. Here, we got a little bit of work to do here. We've got 5 minus, we're going to extract this I. We're going to break 12 into 4 times 3 and extract the 2, leaving 3 as a leftover. So we got 5 minus 2i radical 3. A plus, technically plus or minus, B, this is part of the B and that's part of the B, I, A plus BI. Okay, now what about this one? You'll especially get an answer perhaps like this on doing finding an inverse of a problem, but sometimes you do. Now I'm going to make up a silly word in a moment to deal with this. This number has a common denominator of 3 here. Well, in order to work this and get it into A plus BI format, we must uncommon denominatorize. Or in other words, break this 3 under each component element. Now, if you can reduce, then you must. 6 divided by 3 is 2. 5/3 will reduce I, A plus BI format. Another one, in this case, again, we can't use this common denominator. We have to do a breakout, like so. We have to reduce the 2/10. We also have to reduce this 2/10. So we get -1/5 plus radical 2 over 5i. More examples here. This becomes 7i, so 4 plus 7i. Here, this becomes 3/7 minus 8/7 I. This one, you're going to have to do a reducing on the front end, but anyway, it becomes 10 over 20 plus -5i radical 3 over, I better show that one. Okay, 10 over 20 plus radical -75 over 20, Ultimately, this will reduce to 1/2. We extract the I, leaving 25 times 3 over 20. We extract the 25 over 20 and bring down the 1/2. This would be your final solution on that one. Powers of I. We're going to be working with these. There is a pattern to how you solve these. This is where we're going to take up in week 2.2. Right now we're week 2.1. So this is where we'll take up in our next class period. Have a good day.